Welcome to day 5 on the virtual Ascent field trip. We actually moved north of Ascent now and we're standing at Sango Bay. This is on the north coast of Scotland. The next stop to the north of us is the North Pole and the Arctic Circle. As you can see, the weather is pretty wild out there. This area here is the northernmost extension of the Moine thrust zone, which comes up through here. And it's a very important region historically, because in the 1880s, this region here was the first place that not only were thrusts defined, but also the rock Mylonite. And it stems from the original James Nicol interpretation of the allochthonous nature, the thrusted nature of the Moine schist over the foreland, as opposed to the traditional Murchison implication, which was a stratigraphic contact. So James Nicol was really the first one in the 1860s to say that this was thrust, and various people, including Callaway in 1883, first defined and recognized that Mylonites were indicators of very heavy crushing, recrystallization, and what they called mylonitization along major tectonic boundaries. So we're going to see some of these later on round at Erebol and Sango Bay, but the importance of this area here in Sango Bay and at Farrad Head is that these are the two westernmost extensions of the Moine Mylonite, which means that the Moine thrust must have initially gone at least 15 kilometres to the west from where it is exposed along Loch Erebol. And if I show you a cross section, a very rough sketch of a cross section across this region here, we can see you would expect the east dipping Moine thrust to be way up in the air, but it's actually exposed down here on Sango Bay and at Farrad Head because the Moine thrust is down faulted successively along these late normal faults. And we are now sitting here at Sango Bay. There's another normal fault that drops down Farrad Head, and the distance from there to Erebol is about 15 kilometres. So these normal faults are nothing to do with the Scandian Caledonian orogeny, the phase of thrusting that brought the Moine thrust over. These are much later. There's two phases of extension, one in the Devonian and one in the Permo-Carboniferous. And these faults extend way offshore into the basins of the West Orkney Basin and the West of Shetland Basin, which are important regions for oil and gas exploration. So these normal faults are beautifully exposed on the coast in the distance over there, and we will examine one of these normal faults, this one here at Sango Bay. If I take this sheet here, this is a detailed, slightly more detailed section across the Sango Bay beach, and we can see the major normal fault exposed at the east end of the beach, and it's dropping the Lewisian Mylonites down by quite a considerable throw to be exposed on the beach side here. The Lewisian Mylonites are overlain by a very important rock called the oyster shell Mylonites, which are really biotite, muscovite, chlorite, phylonites. If I go up successively through the strain, you go from a shale to a slaty cleavage, a slate, into a phylonite, which is a mica-rich green-schist facies deformation fabric, into eventually a Mylonite. So these oyster shell Mylonites could have been traditionally interpreted to be derived from the Lewisian, but they could equally well be derived from some sort of shaly unit like the Fucoid beds. There's another unit, the quartz Mylonites, which are exactly the same as we've seen down at Ascent and Loch Erebol. And these all overlay the foreland, which in this region is the Durness limestone, the lower Ordovician limestone. And this is the thickest succession of that basin exposed. So what we're going to do is go down to the beach at the east side, look at this normal fault, and then successively look through the Mylonite section from the Lewisian to the oyster shell phylonites, to the quartz Mylonites, and finally to the foreland Durness limestone beneath. We are sitting straight on the Sango Bay fault, one of these steep normal faults that is dropping down the Moine thrust towards the west. And on the footwall of this normal fault, the normal fault is aligned steeply like this. I've taken a remote strike and dip back there, getting a strike of almost north-south and a dip of somewhere between 60 and 65 degrees. I'm going to check that here actually on the outcrop. But before we do that, we're looking at the rocks actually on the fault. And here, the footwall of this fault is all Durness limestones, part of the Durness sedimentary basin. And this thick sequence of limestone sits unconformably directly on the Lewisian gneiss. So the Torridonian and the quartzites and the pipe rock is all missing here beneath a major unconformity beneath the Ordovician limestone. So limestone on the footwall, and on the hanging wall of this steep fault is the Mylonite sequence that we're going to walk through after this. So this fault is a late brittle feature. It's nothing like the ductile Mylonites that we'll see later on, the earlier ones on the Moine thrust. This is a much later normal fault that is dropping down the whole Moine thrust. And on this brittle fault we can see a breccia. This is a typical fault breccia associated with brittle deformation at high structural levels on a fault. Now I'm going to just check that the remote dip I had, the angle of dip on this fault is correct. And this is a very irregular surface. It's not a nice bedding plane like we've seen, for example, in the pipe rock. So I've already taken a remote strike and dip on this fault by lining it up with my eye as I walked along. And I'm now going to check it with the outcrop. And where you have an irregular outcrop like this limestone, it's not easy to put it on a flat bedding plane, for example, like the quartzites or the pipe rock, use any flat board. You can use a mapping board or a piece of wood or whatever you want. Just make sure it's flat and it's aligned along the plane that you're measuring. Now this is any planar feature. It can be bedding in a sedimentary rock or schistosity in a metamorphic rock. It can be a cleavage plane, and in this case it's a fault plane. So there are two measurements you need to do to record the strike and the dip of any planar feature. There's two methods of doing it, and they're both very, very similar and very, very easy. The first one is simply to take a strike direction. The strike is the planar where a horizontal plane intersects the bedding plane or the fault, and the dip is at 90 degrees to the strike. So you can take a strike, you move it around until your compass is perfectly horizontal, and you can take a dip by moving this around and recording the dip direction. Then you move your compass clino back to 90 degrees, which is there to get the dip. Make sure that the arrow is hanging freely, and you rotate your clinometer around until you get the angle of maximum dip. So that is the dip direction, that is the strike direction. Strike, dip. And then you record the strike as a figure, 0 to 360, and the dip as a number, the angle of dip. In this case, the fault is pretty much north-south, and the angle of dip is exactly 62 degrees towards the west, towards 270. So there you can record it as the strike and the dip. If you do that method, you must record the direction because it could be dipping this way or that way. So in this case, it would be 0, 1, 180 degrees north-south, 62 degrees west. Or you can record 62 degrees west towards the azimuth, which is the direction of dip. And that's all you need to record. Strike, dip, direction.
Further down the beach, we now get a chance to examine the rocks that are in the hanging wall. These have been dropped down onto the beach and now they're exposed. And this locality gives us a really nice example of a sheared Lewisian gneiss. Now we have the different colours here, as we've seen in previous outcrops. The light coloured components are most likely a TTG gneiss, and the dark coloured components are most likely a sheared mafic gneiss. but instead of having the granulite and amphibolite facies assemblages we've seen previously, the mylonitization here occurred at slightly lower temperatures still, and it's more like an upper greenschist facies, lower amphibolite facies assemblage. In the pale coloured gneisses, instead of having orthopyroxene and hornblende, we will have lower temperature minerals, biotites, quartzes, feldspars, maybe some chlorite too. In the dark coloured gneisses, instead of having clinopyroxene, orthopyroxene and garnet, such as in Scauri Moor, we have minerals dominated by chlorite, actinolite and some feldspar too. Now all of these rocks have been intensely sheared, and they will have foliations that show the direction of transport, which is leading off towards the west.
So these oyster shell mylonites are structurally above the Lewisian mylonites we've just seen in the previous locality. And this is composed almost entirely of muscovite, chlorite, low temperature greenschist facies minerals with bands of quartz. So this has been previously, is usually assigned to being a metamorphosed, altered Lewisian basement gneiss, but it could equally well be a metamorphosed pilitic metasedimentary rock, because it's almost entirely made of muscovite and chlorites and micas now. But the beautiful thing about this rock, picked out in the light, are the two fabrics, the C and the S fabrics. So if you remember from the Moine thrust, the S stands for schistosity, which is the main metamorphic fabric, and the S fabric here is this one that curves around in a S-shaped bend, and it's bounded on the top and bottom by these fabrics, which are horizontal, and these are the shear fabrics, the C fabrics. C stands for Césalement, shear. So you have the C fabrics and the S fabrics, and the S fabrics are bounded by C planes. So you have hundreds of different C planes here. There's one there, one there, one there, one there, one there. The whole face is indicative of C fabrics. And the curvature here indicates a top to the west sense of shear, ductile sense of shear. When we're talking about vertical faults, we talk about right lateral dextral or left lateral sinistral. When we're talking about thrust faults, terminology is top to a direction. And this is the Moine mylonites, the ductile Moine mylonites, which indicate a top to the west sense of shear. So with these mylonite fabrics, the most important thing to do is firstly to determine a sense of shear. So we've looked at the C and the S fabrics here and determined a top to the west sense of shear. So really you need a two-dimensional outcrop in order to make sure that you're looking straight along the transport direction. But if I take a strike on this, the direction of that C fabric is 240 degrees, which is west, just south of west. And that fits with all of the structures across the Moine thrust zone. So this is a sample here taken from this outcrop some time ago and taken back to the lab and made a polished section of. And here we can see the crenulations of the micas and the quartz bands within the mylonite, and you can get a beautiful indication here of the folding, the very small scale folding that is associated with these mylonites. Sometimes these can be completely isoclinal. In this case, they're very tight. The other thing that you can do, this is another sample taken from an outcrop just along the beach. You can look at these same fabrics, which are beautifully folded. And here you make the mylonite fabric first, and then you fold the mylonite fabric. And you'll see if I tilt the sample, there's a very prominent crenulation cleavage. So this is another thing that you can measure. Crenulation cleavages can be formed by either bedding cleavage intersections or two cleavage intersections, or they can be lineations related to the direction of transport. In this case, the lineations will be going west, parallel to the direction of transport. Okay, to sum up this outcrop, this is a rock called the oyster shell Mylonites, and this dates back to 1883 when Lapworth first defined the term Mylonite. These are rocks which have been thought to be derived from a protolith lithology in the Lewisian gneiss, in which case all the original crystallization and minerals have been totally recrystallized. The grain size has been greatly reduced and they've totally altered to micas, mostly muscovite and chlorite and ribbons of quartz. Alternatively, this rock could have been derived from a mesosedimentary rock, something like the fucoid beds that we've seen in the Ascent window. And at greater temperatures, this would have eventually become a pilitic rock. In some places, they have garnet crystallizing in the Mylonite, but very rarely. So during initiation of the Moine thrust, the first thing to happen was that these Mylonites formed deep down in the middle crust at temperatures between at least 350, probably as high as 550 degrees centigrade, by ductile shearing along the Moine thrust. And that involved both pure shear compression and simple shear shearing. And it's the simple shear that has created the C and the S fabrics during emplacement. The emplacement direction we've determined is top to the west through looking at the C and the S fabrics. These are repeated right through this entire sequence. Okay, we're now at the western end of Sango Bay and we're going down structural section from the Lewisian Mylonites at the top to the oyster shell Mylonites that we've just seen, and we're now looking at the quartz Mylonites. These are Mylonites derived from the basal quartzite unit, the Cambrian section, and this is at the structural base of the Mylonite section. If I pan down here, the Mylonites actually sit directly on top of the Durness limestone. That's on the stable foreland. So this point with my hand on is the Moine thrust. Now people map the Moine thrust in different places. Some people map it at the bottom of the Mylonite section. Some people map it at the boundary between the quartz Mylonites below and the Lewisian Mylonites above. And some people map it at the top of the Mylonite section. It doesn't really matter where you map it, what name you call it, because these Mylonites derive from deep in the crust, and as they're ramping up towards the Earth's surface, they go from the ductile zone to the brittle zone. So this Moine thrust here is a brittle fault superimposed on a deeper, earlier ductile deformation. What I've drawn here is a restoration of the Moine thrust zone to illustrate the various levels of thrusting that we've seen. So we've spent today walking across the Mylonite zone, and the Mylonites were formed in the very first instance of the Moine thrust, deep down here in the hinterland, and as they were brought up, they were riding over successively different lithologies. So we have Mylonites derived from the Lewisian basement, we have Mylonites derived from the Cambrian quartzites, and we have Mylonites derived from the Durness limestone. So what we've seen up here in Sango Bay is the early formation of the Mylonites and the ductile CS fabrics right up to where the Moine thrust lies over the stable foreland. And we've seen up here in the last outcrop quartz Mylonites sitting on top of the Durness limestone. And that Durness limestone is on the stable foreland beneath the Moine thrust. So on a restoration, thrusts follow flats and ramps, putting older rocks over younger rocks, and they climb from deep ductile positions of the crust right up to shallow levels until they hit the surface where the toe of the sole thrust rests directly on the foreland. So we've left Ascent, the Ascent window, and we've covered the Moine thrust around the Ascent window. We've looked at 2 days at the Lewisian, one day at Scourie on the granulites, one day at Achmelvik on the amphibolite overprint with the Scourie dikes between. And then yesterday we looked at the Sango Bay Moine thrust Mylonite section. What we're going to do today, this is the last day of the field trip, and we are looking at the far north coast of the Moine thrust zone. So this is the northern Loch Eriboll region of the Moine thrust. The next stop out there is the North Pole. There's no land between us and the Arctic Circle. And that's Whitten Head, way in the distance, which is where the Moine thrust goes out to sea. What we're looking at here is one of the classic areas. We're not going to see it on this video because it takes too long to get there, but we will give you a geological field map across this region right in front of me. And what we want you to do is to use the structural and stratigraphic data that you've been given on the PowerPoint to construct a cross-section. You may not have all the detail you need, but you need to use your common sense and logic to figure out what's going on. Use the strikes and dips given on the field trip, on the field slips. Let me just point out the geology to you here. So Loch Eriboll is over there on the west, on the coast, and the coastal strip is the classic section of the imbricate structures above the sole thrust. Those imbricates are where the sole thrust climbs to the higher stratigraphic level. So they are dominantly composed of fucoid beds, grit, and Durness limestone, endlessly repeated. There's about 10-12 repetitions just exposed along the coast. Basal quartzite, pipe rock, fucoid bed, grit, and Durness limestone, and thrust repetitions of those units. On the hill straight ahead of us, that top of the mountain there is called Ben Helam. And Ben Helam is in the quartzite. You can see the quartzites are dipping off to the east, about 20 degrees, but there's far too thick a unit of quartzite there for the known stratigraphy that we've measured on the foreland. So the reason for that is that the whole quartzite section has been repeated. There's at least 4 thrusts between the lake and Ben Helam, which are repeating the whole unit: basal quartzite, pipe rock, fucoid, thrust, basal quartzite, pipe rock, fucoid, thrust. And that is always putting older rocks over younger rocks. The fucoid bed acts as the detachment above the duplex. So from swinging around from west to east, towards the right, you come off Ben Helam, and you can see the strike direction of all of the thrust sheets, and the bedding is in this direction, off to the east. The next crag around, in the middle distance over there, is the Lewisian. So that is where it was first discovered in 1883 that the Lewisian was thrust over Cambrian Ordovician rocks. That's called the Arnaboll thrust, which is equivalent to the Glencoul thrust in Assynt. And that is putting Lewisian over all of this Cambrian Ordovician section in front of us here. Above the big crag of Lewisian gneiss, right on the skyline, in the sunlight, that green strip, is the base of the Moine schist. So the Moine thrust is roughly along the sunset green strip in the far distance. And the dark, foreboding-looking hills on the skyline are all Moine schist. This is the type locality for the Moine schist. It's called Moine, which is Gaelic for bog, and it's very appropriate because all of that land is deep, deep bog. So we have the Moine thrust at the structural top in the east with the Mylonites, the Arnaboll thrust carrying a slice of Lewisian above that, and then 1, 2, 3, 4, at least 4 or 5 thrusts repeating the quartzite unit, and all of that is put on top of the sole thrust, where it ramps up to repeat all the younger stratigraphy, the fucoid beds, grit, and Durness limestone. The sole thrust runs out into the sea in Loch Eriboll over there. So this is a very nice section where the entire Moine thrust zone is condensed into one section. And what we're going to do on this exercise is to give you the field data in terms of the field mapping with all the structural data on, and we would like you to construct a cross section across the Moine thrust zone. Now there's one other thing to add to the whole of this story, which is what happens above the Moine thrust. In other words, the whole of central and eastern Scotland. That is the metamorphic hinterland. Those rocks are all metasedimentary, and they are resting again on Lewisian inliers. So the Lewisian is both on the foreland, in the Moine thrust zone, and at the deeper structural levels of the Moine. The Moine are a very thick sequence of metasedimentary rocks, dominantly mesosamites, a few mesopelites, and very rare granites, Caledonian granites, further over in eastern Scotland. We know from looking at the metamorphism that the metamorphic grade increases as you go along the north coast from west to east, and yet the structural dip is off to the east, which means that the metamorphism above the Moine thrust on a regional scale is upside down. How do you get inverted metamorphism? There's basically two ways. You either thrust a hot sheet over a cold sheet, like you would do, for example, underneath an ophiolite, or you could have right way up metamorphic isograds, which are subsequently folded and thrust, like we see in the Himalayas. There are various models to explain the metamorphic isograds in the Moine, but it's almost certain that the Scandian metamorphism in the Moine, the Silurian metamorphism, was the hinterland thick orogenic wedge that thins to the west. So we have the Moine thrust in the west and a thick metamorphic hinterland to the east. And that has many, many similarities to a present day cross-section across the Himalayas, where you have inverted metamorphism across the main central thrust and a big, thick metamorphic wedge going off to the east in the Himalayas to the north. In the far east of Sutherland, in central and eastern Scotland, there is actually a mignonite complex, and these rocks have the highest temperatures of all of the metamorphism within the Moines. So you're going from a sillimanite Cape feldspar mignonite down structural section as you go towards the Moine thrust through all of the isograds, from sillimanite to kyanite to staurolite to garnet to biotite. And the rocks immediately along the Moine thrust and immediately above the Moine thrust are biotite garnet grade. And there's one other point to emphasize in the Moines, that the mountain hidden just over there to the east is one of these huge syenite intrusions, Ben Loyal. It's exactly equivalent to the two major syenites we saw within the Moine thrust zone, Loch Ailsh and Borrolin, and it's pretty much the same age. It's about 431 million years old. So the syenites were intruding in the Moine, within the Moine thrust zone, and as we've seen in the Canis porphyry on the stable foreland. So this whole region had some weird alkaline anomaly in the mantle that produced these very highly alkalic intrusions immediately prior to forming the Moine thrust. And it could even be possible that the alkaline intrusions, the hot alkalic mantle, actually caused the initiation of the Moine thrust. Okay, so the exercise for this, we will give you on the PowerPoint that accompanies this lecture the structural map of this region right in front of me, and we'd like you to know all of your knowledge now that we've looked at in the Ascent window and at Sango Bay in the previous lecture, to construct what you think is a reasonable cross-section from the Searle thrust to the Moine thrust across the whole of the Moine thrust zone. Okay, good luck.